Hi everyone, this is the final video for lecture 8 and it's part 4 of our look into the D block chemistry. In this video I'll introduce coordination complexes, what they are, and then have a focus on naming them. And this will be the basis for the rest of the lectures and the videos to come actually, because now we're going to be looking a lot at coordination complexes, how they form, the bonding and the shapes they make. Let's take a look at how to name them to start with. So when we talk about compounds of D block elements, we usually refer to them as complexes, or sometimes coordination complexes to be more complete. And this reflects more accurately the bonding and what happens in these molecules. So a coordination complex is just a combination of a metal center, so one of the transition metals that we've been looking at, and a ligand. Now these act as Lewis acids and Lewis bases respectively. We've actually looked a little bit at Lewis acid and Lewis base reactions already when we talked about things like a BF3 and BH3 earlier and how they interact with things like ammonia. So to refresh yourself, a Lewis base is anything that donates an electron pair. So in this case we call them ligands. So ammonia can be a ligand, that's the example we've got in the pictures at the bottom. So ammonia is a ligand and it's a Lewis base and it donates an electron pair to the metal. It's these metal centers like nickel in these examples, metal cations, and they act as Lewis acids because they can receive the electron pair from the ligand. And these ligands are generally neutral, things like ammonia, as I said, or water, CO is another one, or they can be anionic, like chloride anions. They'd be not possible to find a cationic ligand because they're not really going to balance with the positively charged cation of the metal. So either neutral or anionic. And ligands coordinate to the metal to give a complex. If these complexes are ionic, if they're charged, such as the examples down here, they're then called complex ions. And to draw the bonding, although I'm sure you can imagine already what it looks like, if you had a nickel cation, so in this case, we'll just say it's nickel 2+, why not? And then we've got ammonia here, NH3, but this has a lone pair on it. Then this lone pair here can form a coordination bond, hence why they're called coordination complexes, to the nickel center. So these bonds are all formed by lone pairs from the nitrogen and not just a normal covalent bond like shared between the nickel and nitrogen. And on this slide I've got a nice example showing what the difference between a complex ion is and a coordination compound and how the two relate to each other. So when cobalt nitrate's dissolved in water, 6 water molecules will coordinate to the cobalt ion and form a complex ion. Now showing what is coordinated to the metal is done by putting them in square brackets. So we can see in the example here, laser pointer, we've got 6 water molecules in the square brackets with the cobalt, and we've got the charge outside the brackets, and this shows that what's in the brackets is complex together, and because it's got a charge, it's a complex ion. Now if you were to crystallize this solution, you'd get a solid compound which is neutral, and it's much bigger. It's got the complex ion, so in the square brackets, then it's also got 2 nitrate groups outside of it, and this is why it's neutral, because these nitrates each have a minus charge, and they balance the 2+ cation of the complex ion. So it's nicely shown here. The whole thing is the coordination compound. So the cobalt with 6 waters and 2 nitrates is the coordination compound. And the bit in the square brackets with the charge is the complex ion. And you can also get coordination compounds consisting of 2 complex ions, and that's what's in the bottom part here. So the whole compound is shown here. So it's a nickel with 6 ammonias and cobalt with 4 chlorides. And each of these in the square brackets is its own complex ion. So the cobalt with the 4 chlorides is within some square brackets and has a 2- charge outside it. That's one complex ion. The nickel complex is another ion with a 2+ charge, and both of them together form a coordination compound. Now there are a whole array of different ligands that are possible, to coordinate to a metal centre. And I've got quite a few examples on this table that's taken from the textbook. So you've got things that we've seen already with water and ammonia. The formula is shown here, and the donor atom's in red. So it's whichever atom is red has the lone pairs on that will coordinate to the metal centre. So we've got water, ammonia, the halogen anions, hydroxide. Also things like pyridine. So we saw this as an example in one of the questions talking about BF3 or BH3, I think, how it would react with it. And then we got some phosphorus and sulfur based compounds as well that can also act as ligands. Now each of these ligands has its own special name when it's coordinated in a complex. So instead of saying water, so this one's chromium with 6 waters, it's actually aqua. And then ammonia is amine, fluoro, chloro for the halogens, and so on. You don't need to know this off the top of your head. In the exam, if you're going to need to be naming coordination compounds, I'll give you these sheets, so you don't need to know all of these off by heart. Yeah, it will help, and I'm sure over time, if you carry on in chemistry, you'll definitely come to know these off by heart. I don't work with coordination complexes so much, but yeah, things like aqua, you just know straight away. But yeah, for the exam, you won't need to know it. There are also some ligands that we call chelating ligands, and there's an example here that I've again taken from the book. And a chelating ligand is one that has 2+ donor atoms. So it's one molecule or entity, such as this pyridine here, but it coordinates in 2 ways. So let's try and draw over this. So you can imagine if there's a nickel here, say, that both of these nitrogens can coordinate to it. So in general, these are known as chelating ligands, and depending on how many centres donate to, how many atoms donate to the metal centre, they also have different names. So these first few at the top here mainly have nitrogens or oxygen donor atoms. These are called bidentate ligands, and that's because they have 2. Some might say it's predictable, but tridentate for like terpyridine. Yeah, it's tridentate. It's got 3 nitrogens coordinating. You can even get some really big ones. There's hexadentate ligand here, where 4 oxygens and 2 nitrogens will coordinate. And if you go back to one of the videos, the very first one actually, where I showed examples of real life transition complexes, vitamin B12 had cobalt in it, and I think that's got a pentadentate ligand in it, so it's got 5 donor atoms to the centre. And then also we've got the abbreviation of how we'd show them in a chemical formula, because obviously it's easy with something like water or ammonia. You can put it in a chemical formula, just put H2 in the brackets, everyone knows what you mean. But trying to put something with so many carbons and nitrogens in a formula isn't so easy. So they've got abbreviations like EN, PN, BP. Again, you won't need to know these off by heart. If they're in the exam, I'll give you this table so you can use it. Now we've seen some of the metals, we've seen complex ions and coordination compounds, and we've also had a look at a lot of the ligands now. So let's have a look at how to put it all together and actually name these complex ions or compounds. So first up, with the ligands, refer back to the tables to get the name of the ligand on coordination. One thing to note is that the negatively charged ligands end in O, so something like chlorine will become chloro on coordination since it's Cl-. Now we can also note how many of each type of ligand there are by using a prefix. So the example down the bottom here, we have nickel with 6 ammonias. So this uses hexa, so then it's a hexaamine. For example, if there were 4 waters, we look up the ligand name in the table. For water is aqua. It would be tetraaqua if there were 4. And then we also include the oxidation state as well. So it's all written as one big word, no spaces. And we have the number of ligands, what the ligand is, the metal, and then its oxidation state as a Roman numeral. And so then this, we've got an example, is hexaamine nickel 2. And that's how we'd write the name for this complex ion here. And when you're writing the formula also, you have the metal and the ligands in the square brackets and the charge outside the square brackets. Now there's a slight difference if what you're naming is anionic. So like what we looked at just then, hexaamine nickel 2, iron is fine. If we've got cobalt with waters and 2+, it's a hexaaqua cobalt 2 iron. However, if it was anionic, so instead of being 2+, say it's 2-, like we've got here, the nickel 4 chlorines and 2-, because the complex is anionic, we add 8 to the end of the name of the metal. So this one, instead of being tetrachloronickel 2 iron, it's tetrachloronickel 2 iron. And this just shows that it's 2-, minus 2 oxidation state. There are a couple of exceptions to catch you out, and these then come from the Latin name. And so copper, instead of being copperate, is cuprate. Gold, iron, silver, they've all got names that relate to the Latin, but hopefully actually are the same as the elemental symbol, or is where the elemental symbol comes from. So they're just the 4 to be aware from with the anionic complexes. Now there's obviously a case sometimes when not all the ligands are the same. So far we've just looked at complexes with 6 waters or 6 ammonias. But what happens if they've got 2 ammonias and 4 waters, things like that? Well, there are a few rules for the naming of that also. But it's interesting because they differ from the writing in words and the writing the formula. So we'll look at each at a time. So if a complex contains more than one type of ligand, when it's named, as in written out, the ligands are written in alphabetical order. So you've got the example here of platinum with a chlorine and 3 ammonias and positive charge. And this is triamine chloroplatinum 2 iron. And this is because the amine comes before chloro in the alphabet. Simple enough. There are a couple of things to note here though, just to reinforce for the naming. What goes in Roman numerals here is the oxidation state, and that's not always the same as the charge. So far when we've seen like cobalt with 6 waters or nickel with 6 ammonias, the charge has been like 2+ and the oxidation state is 2+. But in this case, the charge is only 1+, but the oxidation state of the platinum is 2+. And that's because the chlorine has a negative charge on it. And this brings me nicely to the next point. When we write it in the word form, we see the ammonia ligand first before the chlorine ligand, because A comes before C. But when we're writing a formula, things that are negatively charged will come before neutral ligands. So in this case, the chlorine is a chloride, so Cl-, so that comes first, and the ammonia is neutral, so it comes second. Now, if you've got more than one type of negatively charged or anionic ligand, or neutral ligand for that fact, then the alphabetical ordering comes into the formula as well. So for example here, we've got chromium with some bromide ions and chloride ions and ammonia ligands. And then because both of these are negatively charged, they're before the ammonia, but they go in alphabetical order. And then when you're putting it in the name, it doesn't matter of whether it's charged or not, whether it's an ion, they go in alphabetical order. And finally, there's one other complication that can spring up while you're naming that you have to be aware of, and that's involving ligands that have numerical prefixes. So things like trimethylphosphine or dipyridine, stuff like this. Because then if there are 3 trimethylphosphines, how do we call it? Do we go for trimethylphosphine? Well, in that case, the ligand name is surrounded by brackets and a different prefix is used to show how many of the ligands there are. Instead of going di, tri, tetra, we then go bis, tris, tetrakis, so on. So the example here, we've got a cobalt with 2 chloride ions, and this is the trimethylphosphine that we were talking about up here. So in this case, it's got 2 trimethylphosphines. So when we write it down, the chloro is there first because it's first alphabetically. But then we have bis because there are 2 of them, and then in brackets trimethylphosphine, cobalt 2. And very finally, for coordination compounds, So if they're not ions, if they're neutral, the cation is placed before the anion in both the name and the formula. So in the example here, we've got the nickel complex ion here that's got a 2+ charge, that's named first, and then the 2 chloro ligands with a negative charge are outside it, and they're dichloride at the end there.